Now this is a really crucial reaction. If you like, you can show the whole mechanism for this, or if you're comfortable, you can just show the product, whatever you like.
For this one, I didn't know, do we have the water just pull the hydrogen off of our final step?
Yeah, that would be best. You mean this right here?
Right.
Yeah, there's plenty of water around. All right, well again, you're already really on top of this mechanism. You saw that we were protonating first. Now notice that what type of functional group did we start with here?
Ester.
Ester, so we expect some type of catalyst. Well, here we're using acid catalyst. H3O plus really means in acid catalyzed conditions. Now once this is protonated, it's a lot easier to have the nucleophile attack. Water is not a great nucleophile, but it can attack someone who's protonated. Now, then at this point, you transferred the proton from here to here because you were keeping in mind that this was going to be the leaving group. So again, it's good that you're not losing track of the leaving group. A lot of people here wouldn't know that this has to be the L group, but we knew from the start that this was going to be the L group. Now, one thing you're doing is you're not actually drawing this mechanism. That's okay for your own time, but your instructor is very picky about showing these mechanisms. You actually have to show this oxygen donating electrons to the hydrogen and the hydrogen losing these electrons. They might not show this in the second language book, but your instructor needs you to show the electron pushing for each step. So we'd have to show how exactly how the hydrogen went from the nucleophile to the leaving group here.
Is that okay to do the water that you
Pardon?
did? Is that okay to just do water, like take one off and then
Yeah,
put it on?
this is perfectly fine. The only thing that you can't do is, the part that with your work is you just didn't include the arrows.
Okay.
You got to, so what happened here is, you just said proton transfer. Well, that's okay maybe to save time on your own, but on the exam, if it was a mechanism problem, you actually have to show how the proton moves from one place to the other place. And the way to do that is the way I have it on the board. And then also you have to show how this hydrogen is being taken off. Your instructor doesn't let you just show hydrogen's leaving. Your instructor wants you to show someone taking the hydrogen. Well, a good person to take the hydrogen here would be the water. Good? To review, what type of functional group did we start with?
And Ester.
And what functional groups did we produce?
Carboxylic acid.
Good. And what other functional group?
Oh, I mean alcohol.
An alcohol. When this left, it became an alcohol.
Mm-hmm.
Now, of course, it doesn't look like an alcohol right now, but in the course of leaving, it gains a proton. So again, we have to be flexible and know that things might look different from what they're going to become if they're going to gain or lose a proton. When this leaves, it gains a proton and turns into an alcohol.
Is it possible to do one practice problem from the book that I have?
Yeah, that sounds good. Let's summarize this question first of all. This is called hydrolysis, and that's one of the most important types of reactions you can see. Why is this called hydrolysis? Because we're using water to break this bond. Hydrolysis means breaking with water. Hydro means water, and lysine means breaking. Last semester you learned ozonolysis, which is breaking alkene bonds with ozone. Well, here we have hydrolysis, which is breaking this bond with water, what type of functional group does hydrolysis produce?
A carboxylic acid.
Yeah. Now you could have done that to any of these. We could have hydrolyzed this acyl halide. By the way, where did this OH group come from? Who brought it in? The water, right? But again, it's hard for students to remember that because it doesn't look like water anymore, because it's lost a proton. So it's important to realize that one good way to make a carboxylic acid is by attacking a carbonyl with water. It's hard to remember that because it doesn't look like water anymore, but it looked like water before it deprotonated over here. So suppose we wanted to make this into a carboxylic acid. How would we do that? Well, we would just attack it with water. We don't need any catalyst here because this is very reactive. How can we turn this into the carboxylic acid?
With water.
That's right. How can we turn an ester into a carboxylic acid?
H3O+.
Yeah, just water and a catalyst now. And it turns out we could also have done this base catalyzed. So water plus acid or water plus base. Either of those would work here. And for that matter, how can we turn this into a carboxylic acid?
Water plus base.
Water plus catalyst, basically. Water plus acid or base catalyst. In fact, that's why these are called carboxylic acid derivatives. The definition of a carboxylic acid derivative is something that when you hydrolyze it, you get a carboxylic acid. These are all called carboxylic acid derivatives because if you hydrolyze them, they all give you carboxylic acids. What we're going to be doing a lot of in peptide chemistry is hydrolyzing amide bonds. Hydrolyzing amide bonds. Well, when you hydrolyze an amide bond, what functional groups do you get?
Carboxylic acid.
And?
OH. Oh, yeah, OH.
You get a carboxylic acid. And what's the other functional group that you'll get?
Oh, you'll get an amine.
That's right. Okay, so we're going to be doing a lot of that with peptides. When you hydrolyze an ester, we saw we got a carboxylic acid and an alcohol, because this picks up a proton. But when you hydrolyze a amide, you get a carboxylic acid and an amine. Well, that happens a lot with peptide chemistry. This was acid hydrolysis. There's also basic hydrolysis. If you want, we can go through basic hydrolysis, or I think you said you had a particular question. Should we look at your question? Page 51?
Yes.
All right.
This last one right here. Are these identical? The O and the GBR, is that the same as OH?
Yeah, you might get partial credit for this, but not full credit. So let's talk about what went wrong there.
Okay.
So these are different.
Yeah, I don't understand that.
Okay. That's important, but it'll take us a little bit to understand that. Let's go back to this for a second, because this is related. We know this is a carboxylic acid. Now, carboxylic acids are tricky because remember, they're acids, which means they're willing to lose a proton. But after the carboxylic acid loses a proton, it doesn't look the same anymore. What does a carboxylic acid look like after it loses a proton? Well, if this loses a proton, it would look like this. What this means is, anytime you're doing a problem with carboxylic acids or with carboxylic acids, if a carboxylic acid is your final product, you have to ask what form should the final product take? Should it have the protonated form or the deprotonated form? Well, how can you tell? Well, under acidic conditions, there's lots of protons, so it should take the protonated form. And under basic conditions, protons get stripped away, so it should take the deprotonated form. So let's see how that applies here. When we did this hydrolysis, were we in acidic or basic conditions?
Acidic.
Acidic. So which of these two forms is the correct answer?
The first one.
The first one, which was what we were already saying. But how about if we had done a basic hydrolysis? If we had done a basic hydrolysis, this would have been the final product over here. So we have to watch out for that when we're forming carboxylic acids. If you're forming a carboxylic acid, you have to ask, are you forming the protonated or the deprotonated form? All right. Now, your particular question has to do with what happens when Grignards attack esters. So let's see what happens with that.